Somewhere very far from anything warm, there is a cloud. It is not a cloud in any sense you could stand beneath and watch roll across an afternoon sky. It has no edge you could point to, no color your eye would catch. It is simply a region of space that is, very slightly, less empty than the space around it. Dust and gas gathered here across millions of years, drawn by the faint breath of gravity, settling into something that barely qualifies as a thing at all. This is where we begin, not with fire, not with light, with cold and with quiet, and with the particular stillness of a place that does not yet know what it will become. The cloud is made mostly of hydrogen. Single hydrogen atoms, some paired into molecules, drifting at distances so vast from one another that the cloud is, by any earthly measure, a near-perfect vacuum. There is also helium, inherited from the very first minutes of the universe, and traces of other things. Carbon, oxygen, nitrogen, silicon, iron. All the elements that earlier stars spent their lives making, and then, in dying, scattered outward. This cloud carries the ashes of stars that are already gone. It is worth sitting with that for a moment. The material here has a history far longer than what we are about to watch. It has already been inside other suns. The temperature of the cloud in most places hovers somewhere around 10 to 30 Kelvin. That is 10 to 30 degrees above absolute zero, the point at which atomic motion would cease entirely. On a scale you might recognize, that is roughly negative 250 degrees Celsius. There is no useful analogy for cold this deep. It is not the cold of winter, or of high altitude, or of deep ocean water. It is the cold of the absence of almost everything. Heat is motion, and here there is almost none. Imagine, if you find it helpful, that you are drifting somewhere inside this cloud. There is no up or down, no wind, no sound. The darkness around you is not the darkness of a room with curtains drawn. It is a darkness that has never been interrupted. The nearest star is so far away that its light, when it reaches this place, is scattered and dimmed by the very dust that surrounds you, until it is less than a whisper of illumination. You would see almost nothing. You would feel almost nothing. Time would seem to have stopped, though it has not. Time here moves exactly as it does everywhere else. It is only events that are slow. And yet something is happening, very slowly, so slowly that billions of human lives could pass without any observer noticing a change. The cloud is doing what matter does when it finds itself crowded even slightly more than usual. It is responding to gravity. Every particle in this cloud pulls just barely on every other particle. The gas in a denser region pulls a little harder than the gas in a thinner region. Matter drifts, almost imperceptibly toward the places where matter already is. This process has no drama. It makes no sound, releases no light. It is simply the universe following the only instruction gravity knows how to give. Come closer. The cloud is not collapsing, not yet. Collapse in this context is a word that implies urgency, and there is none here. What is happening is better described as a very gradual thickening. Certain regions of the cloud are accumulating gas at a rate that, measured against a human lifetime, would register as nothing at all. Measured against 10 million years, a pattern begins to emerge. Slight densities become slightly denser. The process feeds itself gently. There are also forces pushing back. The gas has pressure. Magnetic fields thread through the cloud and they resist compression. Turbulence, inherited from ancient events, old supernova shockwaves perhaps, or the slow churning of galactic rotation, stirs the cloud in ways that are not yet fully understood. The balance between gravity pulling inward and these forces pushing outward is delicate, and it is not a balance that holds forever. The cloud also rotates, very slowly. It has angular momentum accumulated over its long history, absorbed from collisions with other clouds, from the general rotation of the galaxy, from forces that acted on its material long before it gathered into this particular shape. This rotation will matter enormously later. For now, it is barely noticeable. The cloud turns perhaps once every 100 million years, so slowly that the word rotation almost loses its meaning. If you were watching from a great distance, with a kind of patience the universe itself seems to possess, you would see nothing move. There is a quality to this cloud that is worth pausing over, which is that it is genuinely ancient by any human measure. Molecular clouds like this one can persist for tens of millions of years, some perhaps longer, before anything decisive happens within them. The materials inside have been drifting since before the solar system existed. Some of the dust grains were formed in the outflows of stars that died billions of years before our own sun was born. When scientists look at such clouds today, they find signatures of this age written in the chemistry. Complex molecules formed over vast timescales in the cold. Molecules that include water ice, carbon monoxide, ammonia, and even simple organic compounds. The cloud is not sterile. It is, in its own very quiet way, chemically rich. The light that does exist here is not visible. It leaks out from the cloud in the infrared, emitted by the dust grains as they radiate away the tiny amounts of energy they absorb. Radio waves pass through freely, carrying the faint signal of rotating molecules, a signal that radio telescopes on Earth can detect from across the galaxy. These signals are how we know such clouds exist at all, because to ordinary light they are largely transparent, and to eyes like ours they would simply be absent. Dark molecular clouds earn their name. They are dark not only in the sense of lacking light, but in the sense of being regions where light itself is absorbed and scattered, blocked by dust, turned back before it can travel far. The darkness here is structural. It is possible to feel something like peace in thinking about this place. That may seem strange because it is also a place that is extraordinarily hostile to life, to warmth, to any chemistry that could be called dynamic. But there is a kind of comfort in a place that is simply waiting without need or urgency for conditions to change. The cloud does not suffer its coldness. It simply is cold. Time moves through it the way starlight moves through very deep water. Diffused, softened, present but not pressing. Astronomers describe a condition called Jeans instability, named for the physicist James Jeans, who worked out early in the 20th century the relationship between a cloud's mass, temperature, and density that determines whether gravity will eventually win. When a cloud, or a region within a cloud, has enough mass concentrated in a small enough volume, the thermal pressure of the gas can no longer hold it up. It begins to collapse under its own weight. The cloud we are watching has not yet reached that threshold everywhere within it, but the slow thickening continues. The regions of slightly higher density are becoming the seeds of something. Not yet. Not for a long time yet, but the conditions are assembling themselves, the way frost assembles itself on a cold morning, grain by grain, without anyone deciding it should. There is no sound in space. You likely already know this, but it takes on a different texture when you hold it against a place like this cloud. Sound requires a medium dense enough to transmit pressure waves, and the cloud, despite being one of the denser regions of the interstellar medium, is still so thin that sound, in any practical sense, cannot propagate through it. The turbulence here is real, but it is not audible. The shockwaves from distant supernovae pass through as pressure variations in the gas, moving at speeds far below what we would call sound. This is a silent universe, in almost all of its volume. This cloud, in particular, exists in a silence so complete that the word silence is hardly adequate. And so we remain here in the cold, in the dark, at the very beginning of something that has not yet decided to begin. The hydrogen waits. The dust waits. The slow turbulence stirs without arriving anywhere. Gravity whispers its single, patient instruction across distances too large to hold in the mind. Nothing is rushing. Nothing is building toward a moment. There is only the gradual accumulation of conditions, the quiet thickening of a region that is marginally, barely, just slightly more inclined toward its own future than it was before. If there is a lesson the cloud offers, It is something about the relationship between time and change. We tend to imagine that things which will eventually become dramatic must have dramatic beginnings. But here, the beginning of a star is almost indistinguishable from emptiness. A few more atoms per cubic centimeter than the surrounding void. A temperature a few degrees colder than the regions on its edge. A very slight gravitational preference for collapse over expansion. That is all. That is everything. That is the whole of what stands between a cloud and a sun. For now, though, the cloud rests. It has been here for millions of years before this moment, and it will be here for millions more. The galaxy turns slowly around it. Other stars elsewhere go about their own long lives. The universe expands imperceptibly in every direction at once. Here, in this particular region of cold molecular gas, nothing announces itself. There is only the dark, and the cold, and the very slow, very patient pull of everything toward everything else. That is enough for now. That is where the story starts. Somewhere in the cloud, something is beginning, not loudly, not with any announcement at all. A small region of gas and dust has grown by the barest margin, slightly denser than the space around it. That is all that is needed. Density is a quiet thing. It is not a force you would feel standing nearby if standing nearby were possible. It is more like a preference, a gentle leaning. Where matter is slightly thicker, gravity is slightly stronger, and so more matter drifts, unhurried in that direction. More matter means more gravity. More gravity means more matter follows. The whole process is less an event than a mood, a slow settling of inclination across distances that take light years to cross. Imagine you are drifting, weightless at the edge of this region. You would see almost nothing. The cloud here is still dark, still cold, still so thin that a cubic meter of it contains only a few thousand molecules, which sounds like a lot until you consider that the same volume of the air around you right now contains something closer to 10,000 trillion molecules. The cloud is not empty exactly, but it is close. What is here, though, is time. There is so much of it. And given enough time, even the gentlest tug adds up to something. The dust grains are small, smaller than the particles of smoke that drift from a candle flame, many of them. They are made of silicates and carbon compounds, some of them coated in thin films of ice, water ice, or frozen carbon monoxide, depending on the temperature and the local chemistry. They have been here for a long time before this story begins. Some of them were forged inside older stars, stars that lived and died before this region of the galaxy had any reason to remember them. The star you are following has not yet formed, but some of the material it will be made of is already ancient. These grains do not move quickly. Their speeds relative to one another are gentle, sometimes only tens of meters per second, sometimes less. When two grains drift close enough, they may stick. Not always. The physics of grain collision is complicated and not entirely settled even now. Some collisions result in growth. Some result in one grain chipping a fragment from another. But on balance, over long stretches of time, the tendency is toward accumulation. You might picture it as sediment, the way fine silt slowly settles through still water in a glass, except that here there is no water and no glass, only the vast, patient quiet of space, and the slow migration of particles that are in no hurry at all to become something. The region that is collapsing is not perfectly smooth. Molecular clouds are turbulent on their own scales, threaded with currents and density variations, the way the surface of a very still lake is not quite flat if you look closely enough. These variations matter. They are not obstacles to the collapse, but they are complications. Different parts of the cloud collapse at different rates, at slightly different angles. The process has a texture to it, uneven and gentle and real. Meanwhile, the temperature here remains very low, somewhere around 10 to 30 degrees above absolute zero in most estimates of regions like this one. That is cold in a way that is difficult to hold in the mind. At those temperatures, the thermal motion of particles is extraordinarily slow. The chemical reactions that are possible are limited, narrow, patient. Molecules that would never form in warmer environments can persist here, can build up over millions of years. Carbon monoxide, ammonia, water, formaldehyde. Even in some observations of clouds like this one, traces of more complex molecules, the early ingredients of a chemistry that will matter later, much later, in stories that are not quite this one. The dust and gas are falling together now, if falling is the right word for a motion so gradual, inward toward the region of highest density, which is itself shifting slightly as the whole system slowly rotates. There is rotation because there is almost always some small amount of angular momentum in any large parcel of interstellar gas, a residue of turbulence and the motions of the galaxy as a whole. That rotation is nearly imperceptible now, but it will matter. In time, it always matters. Imagine you are drifting again, closer this time, close enough that if you had instruments sensitive enough, you might begin to detect a very slight increase in the density of the gas around you. Still not visible to the eye, still dark, still cold. But the cloud in this small region is no longer as it was. Something has begun to differentiate itself from its surroundings. Slowly, the way a thought takes shape before there are words for it. At the center of the collapse, a structure is forming that astronomers call a dense core. It is perhaps 1/10 of a light year across, perhaps a little more. That is still an enormous distance by any human measure, roughly 6 trillion kilometers, but it is small for a molecular cloud. which might stretch for dozens of light years in every direction. The dense core is a concentration, a pooling. It is where the first real commitment to becoming a star begins to take shape. It is still made mostly of hydrogen, as almost everything in the universe is, with helium as the second most common ingredient, and then a scattering of heavier elements in proportions that reflect the history of the galaxy up to this point. The dust grains make up only about 1% of the total mass, perhaps a little less, but they play a role larger than their mass would suggest. They help the cloud cool, radiating away heat as infrared light, allowing the collapse to continue without the core warming up too quickly and halting its own contraction. Cooling is, quietly, one of the most important processes happening here. You would not see any of this with your eyes. There is no light being produced. There is only the soft glow of thermal radiation at infrared wavelengths, detectable only to instruments of a kind that were not built until very recently in the history of the beings who eventually emerged on a small planet in a later part of this same story. What you would experience, if experience is the right word for a drift through near vacuum at 10 degrees above absolute zero, is an almost total and enveloping silence. A dark so complete it would feel like something more than the absence of light, and a cold so thorough that even the concept of warmth would seem like a distant rumor. There is something in that, if you let yourself rest in it. The universe does not need to be observed to proceed. The collapse continues whether or not anyone is watching, whether or not any consciousness has yet arisen anywhere in the cosmos to name what is happening. Gravity does not require an audience. The grains are gathering. The gas is thickening slowly inward. The dense core is deepening, pulling more of the surrounding cloud toward its center. In some simulations, this phase of collapse can last for tens of thousands of years. In some regions, longer. It is not a fast process by any measure of time that feels intuitive. But it is happening, and it will not stop now. The balance has tipped, quietly and without ceremony, past the point where the outward pressure of the gas can resist the inward pull of gravity. That tipping point has a name. Jean-Baptiste Biot explored related ideas, but the theoretical framework was largely developed by James Jeans in the early 20th century. When a cloud of gas reaches a certain combination of mass and temperature and density, it becomes gravitationally unstable. The threshold is called the Jeans mass, and the collapse that follows is sometimes called Jeans instability. It is a soft name for a slow and irresistible process. Irresistible, but not quick. There is no drama in it, just the long, patient arithmetic of gravity, adding up its small increments across distances and timescales that dwarf any frame of reference a human life can hold. The dust grains settle. The gas continues to fall inward. The core grows a little denser, a little warmer at its very center, though warmer here means rising from 10 degrees above absolute zero to perhaps 20 or 30, which is still a cold that would be lethal to anything familiar. The infrared radiation carries heat away into the surrounding cloud. The collapse sustains itself. Somewhere in this cloud, in this particular dense core, in this slow and unphotographable dark, the material that will become a star is making its way toward a center. It does not know this. It is not moving with any purpose that can be named. It is simply following the oldest instruction in the universe, the one written into the geometry of space and mass, which says, "Where there is more, more will come." That is enough for now. The grains are gathering. The cloud is patient. The dark is full and still and very, very cold. Rest here a moment if you like. Nothing is required. There is time. Something is changing, though you would not know it to look. The core of the cloud has been pulling inward for a long time now, longer than any civilization has ever existed to measure it. And the material falling toward the center has been accumulating the way sediment accumulates at the bottom of a still lake. Slowly, without announcement, the density at the heart of this collapsing region has crossed a threshold that has no dramatic name, no single moment you could point to, but the physics of the place have shifted nonetheless. This is where the protostar begins. Not with light, not yet. The first thing that happens is heat, and the heat is hidden. As the gas falls inward, it compresses. Compression generates warmth. The same way a bicycle pump grows warm in your hand when you push the air down quickly, except here the hand and the pump are gravity, and the motion is slow, and there is no hand at all. The warmth builds at the center of this dark knot of gas and dust, invisible to anything outside it, because the material surrounding it is still thick enough to swallow any photon that tries to leave. This phase, if you were watching with infrared instruments from somewhere very far away, might show you a faint warmth in the data, a slightly elevated temperature in a region that had previously shown none. You might almost miss it. You would not see a star. The object forming here is called a protostar, and the name is precise, in the careful way that science prefers precise names. Proto meaning before. A star before it is a star. It is doing many of the things a star will do, gathering mass, generating heat, beginning to push back against its own inward pull. But it has not yet reached the condition that earns it the full title. That condition requires a temperature at its core so high that hydrogen atoms stop being merely hot and begin to fuse. That moment is still ahead. For now, imagine you are drifting at a very great distance, looking toward this region of the galaxy. The molecular cloud is enormous, dark against the faint background of more distant stars, and within it there are perhaps dozens of similar collapses happening at once in different cores at different stages. Some will produce stars like the one we are following. Some will not gather quite enough mass and will end as something dimmer, cooler, a brown dwarf, a failed star that never quite lights. The cloud itself does not distinguish between these outcomes. It only falls. The protostar at this stage is larger than the star it will become. This is worth sitting with for a moment because it runs against intuition. We tend to think of things growing larger as they mature, but a protostar is a puffed, diffuse thing, spread across a volume that might be several times the diameter of what it will eventually settle into. It is warm at the center, yes, but that warmth is distributed through a great deal of loosely packed material, and the object has not yet found its equilibrium. It is still falling into itself. It will continue to do so for a long time. The outer layers of the surrounding cloud are still raining inward, adding mass, adding pressure. This process is called accretion, and it is patient. Material arrives at the protostar the way guests arrive at a very slow gathering, one after another, over thousands and then hundreds of thousands of years. The protostar accepts all of it. It grows heavier. The pressure at its center climbs. There is something else happening too, something that shapes how this whole scene looks from outside, should you have any way to look. As material falls inward, it carries angular momentum with it, a property of spinning and moving things that physics conserves the way a careful accountant conserves figures. The original cloud was not perfectly still. It had a slow, almost imperceptible rotation, the way most large things in space do, a consequence of the accumulated tugs and nudges of nearby masses over long spans of time. As the cloud falls inward and the core condenses, that rotation speeds up, in the same way that a figure skater, pulling her arms inward, spins faster. The protostar does not simply gather a perfect sphere of gas around it. It gathers a disk. This disk is called a protoplanetary disk, and it is one of the quieter miracles of physics, though miracle is perhaps too charged a word. It is simply what angular momentum requires. The material that cannot fall straight inward instead circles, and the circling material flattens into a plane, and the plane becomes dense enough that, in time, smaller things may begin to form within it. We are not there yet. We are early. But the disk is present, and it matters, and it is there whether or not anything will ever orbit within it. From very far away, if you had instruments sensitive enough, the protostar at this stage would glow faintly in infrared wavelengths. The warmth from within is being absorbed by dust and re-emitted at longer wavelengths, redder and slower than visible light. And this is how astronomers find these objects in our own galaxy today, not with their eyes but with instruments that read heat. There are catalogs of protostars in our galaxy. Some of them are not so different in age from the one we are watching, relatively speaking, and yet they are so far away that we see them as they were when the light began its journey, which may have been before anything alive on Earth had learned to wonder about them. The dust around the protostar is still very thick. Think of it as a curtain drawn around something not yet ready to be seen. The protostar inside is warming slowly, contracting slowly, building pressure slowly. And all of that slowness is wrapped in a layer of material that absorbs and scatters and re-radiates, turning any light produced into a gentle, diffuse warmth that spreads outward into the surrounding cold, without illuminating anything in particular. If you were somehow very close inside the disk, somewhere in the dark outer regions of the infalling material, you might feel a faint warmth in one direction. You would not see a sun. You would see darkness. Perhaps a faint red glow, the color of a coal that has nearly gone out. Perhaps nothing at all. This phase lasts a long time. Estimates vary, as they tend to with processes this old and this remote, but something on the order of 100,000 years is a reasonable figure for the early accretion phase, the period during which the protostar is still building mass from its surrounding envelope. Some stars take longer. The uncertainty is gentle, meaning the numbers are well constrained but not perfectly so, and the variation between individual objects is real. Stars, even before they are stars, are not identical. The protostar grows. The core temperature rises, 10,000 Kelvin at the center, 100,000, a million. These are not temperatures that have easy analogies. The surface of the Earth at its hottest natural point is perhaps a few thousand degrees Celsius in a lava flow. The center of this protostar at 1,000,000 Kelvin is simply a different category of heat, and it is still climbing. At some point in this long warming, the protostar develops a strong outflow. Jets, narrow and fast by the standards of what surrounds them, emerge from the poles of the forming star, perpendicular to the disk, and push material outward into the surrounding cloud. These jets are visible in infrared and sometimes invisible light, and they are one of the first signs from outside that something energetic is happening within. They are not explosive in any usual sense of the word. They are sustained, continuous over thousands of years, and they carve long, bright streaks into the cloud called Herbig-Haro objects, named for the astronomers who studied them. If you have ever seen an image of a young stellar object with narrow glowing plumes extending away from a central brightness, that is what these are. They are common. They are part of the process. The jets also help the protostar in a subtle way. They carry away some of the angular momentum that would otherwise prevent more material from falling inward. They are a release valve, a slow exhale, letting the system continue to accrete without spinning itself apart. Over time, the envelope of infalling material thins. The accretion rate slows. The surrounding cloud locally has been depleted by what has fallen in. The disk remains, still circling, still dense in places, but the heaviest rain of material has passed. The protostar is approaching a new phase, one in which it will no longer be fed from outside in the same way, and will have to subsist on what it has already gathered. This is still not ignition. That is still ahead. But something has changed again. The way something always seems to be quietly changing here, in this slow and patient place. The protostar is beginning to clear its own surroundings. Light, real visible light, is starting to leak through the thinning dust. Not much, not yet. But if you were watching from very far away with the right instruments, the infrared excess that has been the only sign of this object for so long is shifting. The dust is warming differently. The envelope is becoming translucent in places. The protostar is not glowing the way a main sequence star glows, with the steady light of nuclear fusion. But it is luminous in its way, warm from gravitational contraction alone, radiating from its surface as a large, cool object does, a slow red-orange warmth, the color of embers seen through fog. It is visible just barely to the universe around it. It has been here, gathering itself for a very long time already. There is no hurry. The next thing will come when it comes. For now, the protostar sits in its thinning cloud, large and warm and quiet, and the disk circles around it in the dark, and everything that will eventually become part of this system is already, in some sense, present. You could rest here too, in this long, slow warmth, in this almost light, and simply wait with it for a while. There is a threshold somewhere deep inside the collapsing cloud of gas, where temperature and pressure finally become sufficient for something altogether different to begin. It does not happen as an event exactly. It does not arrive with any announcement. It simply becomes true, the way morning becomes true, gradually and without a single decisive moment you could point to and say, "There, that was it." The core has been warming for a very long time. Millions of years of slow collapse, millions of years of infalling gas, of pressure building against pressure, of protons moving faster and faster and crowding closer and closer together. And now, in the innermost region of what was once just a cold knot of darkness in a molecular cloud, those protons are moving fast enough, and the distances between them are small enough. That's something the universe keeps quietly available as a possibility has finally become actual. Hydrogen nuclei are fusing into helium. It begins slowly and it remains slow, in the way that almost everything here remains slow. A single proton encounters another proton, and the weak nuclear force has a role to play in this, and one of the protons becomes a neutron, and a deuterium nucleus is briefly formed, and the process continues in steps that particle physicists have traced with great care. The energy released in each individual event is vanishingly small. The sheer number of events is not. Imagine you are drifting near the core, though of course no living thing could be near the core. And imagine you could see what is happening at a scale far below what any eye could resolve. What you would see, if that were possible, is not a fire. Fire is a chemical process, and this is something older than chemistry, something that predates the first molecule that ever formed anywhere. What you would see is more like a kind of deep arithmetic, the universe adding and subtracting at the level of the atom's heart, and releasing, in each small transaction, a quantity of light. That light does not travel freely. This is worth sitting with for a moment. A photon released in the core of a star does not stream outward into space. It travels an extraordinarily short distance before it is absorbed by the surrounding plasma and re-emitted in a new direction, and then absorbed again, and re-emitted again, following a path so tangled and indirect that it may take tens of thousands of years, perhaps longer depending on the star, to work its way from the core to the surface. The light you eventually see leaving a star has been wandering inside it for a very long time. It is old light by the time it escapes. So the ignition of fusion in the core is not something that announces itself immediately at the surface. The star does not suddenly brighten. It continues for now to look much as it looked before, a warm and gradually brightening object in the darkness, shedding infrared light into the surrounding gas and dust. The change is interior. The change is the kind of change that takes time to become visible, which in this place feels entirely appropriate. Something else is happening, though, that has consequences the star will feel more promptly. The energy released by fusion creates outward pressure, a radiation pressure pushing against the weight of all the gas above it, and that weight is considerable. The outer layers of the star are pressing inward, pulled by gravity, and for a very long time during the collapse that inward pull has been uncontested. Now there is something pushing back. This is the balance that defines a main sequence star, and it is being established here, slowly, over time. Not perfectly all at once, but gradually settling, the way a scale settles when the weights on each side approach equality. Gravity pulling inward, radiation pressure and thermal pressure pushing outward. The star finding, over long stretches of time, a kind of equilibrium that it will hold for a very long time indeed. The duration of that equilibrium depends on the mass of the star, and this is one of the gentler ironies written into the physics of stellar evolution. More massive stars burn hotter and faster. A star, many times the mass of our own sun, may spend only a few million years in this balanced state before it exhausts its fuel. A star like the sun has roughly 10 billion years. A smaller, cooler star, a red dwarf burning its hydrogen with extraordinary economy, may remain on the main sequence for hundreds of billions of years, longer than the current age of the universe. The star we have been watching, this particular star in its particular corner of this particular galaxy, will find its own place somewhere along that range. Imagine you are very far away, watching the star from a distance of perhaps a few light years. You would see it now as a point of light, pale and steady. Nothing in its outward appearance yet reveals what has begun inside it. The surrounding cloud of gas and dust, the remnant of the molecular cloud it was born from, still swaddles it in places, and some of that material is still falling inward. Jets of material may still be firing from the poles, clearing paths through the surrounding medium. The star is not yet fully itself, but inside, in the dark and unreachable interior, the process that will define it for billions of years has begun. There is something quietly moving about this, if you allow yourself to dwell on it. The fusion happening in the core is the same process that powers every star visible in the sky tonight, every star that has ever been visible in any sky, every star that has gone dark before any eye existed to see it. It is one of the most common processes in the universe, and also one of the most fundamental. It is how the universe makes helium from hydrogen, and it is how the universe will eventually make the heavier elements in the later lives of stars more massive than this one, and it is how the energy locked inside matter slowly becomes light. That light, wandering through the interior of the star on its long, disordered journey outward, carries something from the core to the surface and eventually into space. It carries a record of what happened deep inside, encoded in its wavelengths, readable in principle by instruments that do not yet exist and perhaps never will. The light leaving a star is a kind of message. It is just a very slow one. The core temperature at ignition for a star of roughly solar mass is somewhere in the range of 10 million degrees Kelvin. This number is worth holding in the mind for a moment, not with alarm or astonishment, just quietly, the way you might hold a stone that turns out to be heavier than expected. 10 million degrees, and that temperature will remain roughly stable for as long as the fuel holds because of the feedback built into the process. If the core gets hotter, the fusion rate increases, which increases the outward pressure, which causes the core to expand slightly, which lowers the temperature, which slows the fusion rate again. The star is self-regulating in a way that is almost difficult to believe without sitting with it for a while. This is what stability looks like at stellar scales. Not perfect stillness, but a kind of dynamic quiet. Small fluctuations, gently corrected. A balance maintained not by rigidity, but by responsiveness. The star breathes, in a sense, very slowly over timescales that make the word breathing feel almost too quick. You might stay here for a while in this portion of the story and simply observe the light. Not the visible light, which is still making its slow way through the interior, but the idea of it. The knowledge that somewhere in the unreachable center of this object, something is happening that did not happen before. Protons are crossing the threshold into each other, and helium is accumulating slowly, a slow deposit of ash at the center of a long fire. And the star is shining in its way, even if that shining has not yet reached anyone who might notice it. The disk of material surrounding the young star continues to evolve. Dust grains are colliding and sometimes sticking, and over long stretches of time, planetesimals may form, and eventually something that could be called a planet, though that is a process for another chapter of this long story. For now, the disk swirls and glows faintly with its own warmth, and the star at its center settles into the rhythm that will define the next phase of its existence. That rhythm is not dramatic. It is not visible in any single moment. It is the rhythm of hydrogen slowly becoming helium, of light slowly finding its way outward, of a star holding its shape against gravity for as long as its fuel allows. On human timescales, nothing appears to be happening at all. And so you might simply rest with that image for a while. The star, pale and quiet in its corner of the galaxy, burning with a patience that exceeds anything we have words for. The light inside it, wandering. The core, warm and steady and doing its slow and ancient work. There is no hurry here. There never has been. A star, once it finds its balance, does not need to announce itself. There is no signal sent, no visible change from one year to the next, or from one century to the next. The light simply continues, steady and ancient seeming even when it is still relatively young. The star settles into a kind of working stillness that will last longer than you can comfortably hold in your mind. This period is called the main sequence. It is not a place, it is a condition. Imagine you are drifting at a very great distance, far enough that the star appears to you as a point of warm light against the dark. You have been drifting here for what feels like a long time, and nothing much has changed. That is, in some ways, the whole story of this chapter. The star is burning. The star will continue burning. and the span of time across which this remains true is so large that ordinary language quietly fails you. For a star of this particular size, a solar-type star, the main sequence lasts somewhere in the range of 10 billion years. Not 10 million, 10 billion. Let that settle for a moment if you like. Our own sun is roughly halfway through this period right now, which means it has already spent approximately 5 billion years in this condition, fusing hydrogen in its core, maintaining its pressure, holding its shape against the inward pull of its own gravity. It will continue doing so for another 5 billion years or so, give or take, before the conditions begin to change. You are, in this moment, somewhere in the middle of a very long and quiet afternoon. The process happening at the center of the star is called hydrogen fusion. 4 hydrogen nuclei are pressed together under conditions of extreme pressure and temperature, somewhere around 15 million degrees Celsius at the core. And what emerges from that process is a helium nucleus, 2 particles called positrons, 2 neutrinos, and a release of energy in the form of gamma radiation. This is the mechanism. It is not glamorous to describe, but it is extraordinarily persistent. The energy released at the core does not reach the surface quickly. It begins its journey as a gamma-ray photon, but the interior of a star is so dense that this photon almost immediately collides with a particle and is absorbed, then re-emitted in a slightly different direction. And then this happens again and again. The photon, or the energy it represents, bounces and wanders through a layer of the star called the radiative zone, in a process that, depending on how you model it, may take somewhere between 10,000 and 100,000 years before that energy reaches the outer layers and begins its final, relatively swift journey to the surface. The light leaving the star right now began its journey as something released near the core a very long time ago, in human terms. There is something almost meditative about that, if you stay with it. The surface of the star, the photosphere, is where the light finally escapes into space. From there, it travels outward at 300,000 kilometers per second, which sounds fast, and is fast, but the distances involved are such that even this speed begins to feel modest. The light that left this star 8 minutes ago is only now, at this moment, reaching a planet at roughly the distance of Earth. Light that left the star 4 hours ago has only just passed what would be the equivalent distance of Neptune. The star exhales light in every direction, constantly, without pause. At the surface, the temperature is around 5 to 6,000 degrees for a sun-like star, producing a light that appears to the human eye as yellow-white, though it contains the full visible spectrum and more. Cooler stars glow orange or red. Hotter stars glow blue-white. These colors are not decorative. They are direct readings of temperature, consequences of physics, wavelengths emerging from the specific energies of the atoms and ions at the surface. You can read a star the way you might read a face, quietly and from a distance, and learn something true about it. The surface of the star is not still, of course. If you could move closer, carefully, and observe it at the scale of individual features, you would see a texture called granulation. Columns of hotter plasma rise from below, spread outward across the surface, cool slightly, and sink back down. Each of these granules is roughly the size of a large country. They form, drift, and dissolve in a matter of minutes. The surface of the star is covered in thousands of them at any given moment, constantly shifting, a slow boil of light. And larger still, there are sunspots, regions where the magnetic field suppresses the upward flow of heat, leaving areas that are somewhat cooler than their surroundings, darker by contrast though still extraordinarily bright in absolute terms. These come and go on cycles that, for our Sun, last roughly 11 years. Other stars have their own magnetic cycles, their own rhythms, their own slow pulses. A star breathes after a fashion. Not dramatically, not in a way you would notice without careful, long observation. But there are cycles, there are variations, there are small oscillations in brightness and in the activity of the magnetic field. The star is not a static object. It is a dynamic system held in a long, stable equilibrium, and within that equilibrium, small things are always shifting. The star also moves, though again, not in a way that would be immediately obvious to you from outside. It orbits the center of its galaxy. For a star positioned something like our Sun, that orbit takes on the order of 225 to 250 million years to complete. This is sometimes called a galactic year or a cosmic year. During the entire period of the main sequence, a solar-type star completes something like 30 to 40 of these galactic orbits. It drifts gently, continuously, through the slow rotating body of the galaxy, passing through regions of slightly varying stellar density, occasionally moving through the spiral arms, occasionally drifting in the quieter spaces between them. The star does not notice this, of course. It simply continues. If there are planets orbiting this star, and there may well be, they are going about their own long, slow business during all of this time. Rocky worlds closer in, if they have the right conditions, might develop chemistry in their shallow oceans, might eventually develop life, might over enormous spans of time develop something capable of looking upward and wondering where the light comes from. Or they might not. The star does not require this to be happening. The star has no investment in the outcome. It is simply producing heat and light and doing so with extraordinary patience. The outer layers of the star are slowly, very slowly, being lost to space as well. A constant stream of charged particles flows outward from the surface in what is called the stellar wind. For a sun-like star, this is a gentle thing, too thin to feel and too sparse to measure easily at a distance. But it is real and it is continuous. And over billions of years, it carries away a small but meaningful portion of the star's mass. The solar wind from our own sun shapes the space around it for enormous distances, creating a bubble called the heliosphere that extends well beyond the outermost planets, a vast and diffuse boundary between the star's influence and the interstellar medium beyond. The star is not perfectly isolated. It is in conversation, in the most gradual and impersonal sense, with everything around it. And all of this, every part of it, continues in the same way for what you might call a very long afternoon. 10 billion years is not a span of time that compresses easily into feeling. If you tried to watch it unfold at human scale, each year of observation representing 1 million years of the star's life, you would still need 10,000 years of watching to reach the end of the main sequence. The star offers no acceleration, no summary, no shortcut. It simply burns, it simply shines. There is a quality to this kind of time that is different from the kinds of time we usually think about. It is not waiting. The star is not waiting for anything. It is not building towards something or winding down from something. It is in the middle of a process that is happening completely, at full expression right now. The core is fusing hydrogen right now. The light is escaping right now. The stellar wind is flowing right now. There is no earlier version of this moment that was more fully itself. This, perhaps, is one of the stranger and quieter gifts that astronomy offers, if you let it settle in slowly. The universe does not share our sense of duration. It has no preference for fast. So let the star shine. Then, in whatever corner of your mind is still attending to this. It does not need you to watch. It does not change when you look away. It is doing exactly what it would be doing whether this narration existed or not, whether you were here or not, whether anyone was here or not. The light goes on. The fusion continues. The granules rise and fall across the surface in their quiet thousands. The star moves in its long, slow arc around the galaxy. Somewhere in the middle of 10 billion years, there is a moment that could be called right now. And the star is in it, as it always is, quietly and completely, without any urgency at all. Something is changing, though you would not notice it from any human vantage point. There is no visible tremor, no signal sent outward into the dark, only a slow interior rearrangement, the kind that takes longer to complete than any civilization has yet existed to measure. The hydrogen at the core is nearly gone. Not gone all at once, not in any event you could point to, but quietly used, the way a candle uses itself without announcement. For billions of years, the star has been converting mass into light, and the light has been holding the star open against its own gravity. And this arrangement has been so stable, so perfectly balanced, that nothing needed to change at all. But hydrogen does not replenish itself. And so, without drama, without warning, the balance begins to shift. What happens next is not a collapse and not an explosion. It is something quieter and stranger than either of those words suggests. The core, now mostly helium, begins to contract. Gravity has always been waiting here, patient in the way that only a fundamental force can be, and now it presses inward on this newly inert material, this helium that cannot yet burn, this ash that still has a future but not yet. The contraction releases energy. This is a detail worth sitting with for a moment. The idea that falling inward produces heat, that compression is itself a kind of burning. The helium core grows smaller and hotter, and the energy released travels outward, and the layers of hydrogen that still surround the core, the hydrogen that was never quite hot enough to fuse before, now finds itself heated from below, and it begins to burn. This is the hydrogen shell. It is a thin region, in cosmic terms, surrounding the inert helium center, and it burns steadily, adding new helium to the core beneath it, like sediment slowly deepening a riverbed. And the energy from this shell, this new furnace just outside the old one, pushes outward with a pressure that the star's outer layers have never quite felt before in this way. The outer layers respond by expanding. Not quickly, not visibly, not even if you watched continuously for 100,000 years. But the expansion is real, and it is continuous, and it will not stop for a very long time. The star is swelling. It is growing outward in all directions at once, at a pace so gradual that the word slow seems almost insufficient, though it is the right word and the only one that fits. Imagine you are very far away, watching through something better than any telescope we have yet built. You might notice, over millions of years, that the star is slightly larger than it was, slightly dimmer at the surface, though brighter overall because the total energy pouring out has increased. The color, too, has begun to shift. It is moving along a spectrum from yellow toward orange, from orange toward a deep and quiet red. Not a dramatic red, not a fire red, but the kind of red you might see in the last light of a long day, diffuse and warm and without urgency. The star is becoming a red giant. This name, red giant, carries a plainness that serves it well. There is no flourish in it. It is simply a description. Red because the expanded surface is cooler. Giant because the outer layers now reach much farther from the center than they once did. If this star were our own sun, and it is not, but if it were, those outer layers would eventually engulf the inner planets. They would reach out past where Mercury is, past where Venus is, perhaps to where Earth is or just beyond. The inner solar system would be inside the star. This is worth imagining calmly because it is not a catastrophe on the scale of the universe. It is simply what stars do. They are not permanent in the way a mountain might feel permanent, or even in the way a stone does. They are processes, sustained reactions, and like all reactions, they move through phases, and each phase leads to the next. The star's surface, now so far from the core, is held only loosely. The gravity at that surface is weak, because gravity falls off with distance, and these outer layers are very far from the dense center. And so the star begins to lose mass. Quietly, continuously, a stellar wind blows outward from the surface, carrying gas and dust away into the surrounding space. Not dramatically, not in visible puffs, but in a steady exhalation, the way a room slowly loses warmth to an open window. This lost material does not disappear. It drifts outward and joins the interstellar medium, the thin gas between stars, where it will remain for a very long time, until something gathers it again. The star is already returning pieces of itself to the reservoir from which it came. Inside, the helium core is still contracting, still growing hotter, patiently waiting for the temperature that will allow something new. Helium fusion requires much higher temperatures than hydrogen fusion, and so there is a long period in which the core simply grows denser and hotter, accumulating heat without yet releasing it through fusion. Some stars will reach that threshold, some will not. The outcome depends on mass, on a number that was fixed when the star was born, when the original cloud collapsed and determined how much material would be gathered into this particular point of light. But that threshold is still ahead. For now, the star expands and cools at its surface and brightens overall, and drifts slowly through the color of embers. Imagine you are drifting somewhere in the space around this star, far enough to be safe, far enough to see the whole of it. The light reaching you now is redder than it was, softer in a way, more diffuse. The star is larger than it was when it was young, much larger, and yet the surface you are looking at is cooler than the surface it replaced. There is something in this that might remind you of age in the biological sense, though the analogy only goes so far. The star has not slowed in the way a tired thing slows. It has changed character. It has become something different, not diminished, but different. The surrounding space has been touched by this. Heavier elements, small amounts of them, are being carried outward in the stellar wind. Carbon, nitrogen, oxygen, the products of earlier burning or the byproducts of the shell reactions, drift away from the star in quantities that are small but not nothing. The space around this star is being seeded very gently, very slowly, with material that was not there before. This is one of the quieter gifts of stellar evolution, the way stars enrich their neighborhoods without intention, without effort, simply by being what they are and doing what they do. The gas they shed becomes part of the next generation of clouds, the next generation of stars, the next generation of whatever forms around those stars. The red giant phase will not last as long as the main sequence did. Nothing does. The main sequence was the long middle, the deep patience of hydrogen burning, and what comes after is shorter and in some ways more eventful, though eventful is still a relative term across millions of years. The giant phase is measured in hundreds of millions of years for a star like this, not billions. It is a phase, not an era. And through all of it, the expansion continues. The surface cools, the wind blows, the helium core waits. There is something in the quality of red giant light that feels different from the earlier white-yellow light of the main sequence, though this is more impression than measurable fact. The light is lower energy per photon, more of it in the red and infrared, the part of the spectrum that carries warmth more than sight. If you could feel this light rather than see it, it would feel like something gentle and pervasive, not the sharp brightness of a younger star, something older in its quality. The star does not know any of this, of course. It has no experience of its own light, no awareness of its own expansion. It simply is, as it has always simply been, a process continuing because the conditions for it still exist. When those conditions change, it will change. When the core reaches the temperature for helium ignition, something new will begin, something that deserves its own attention. But not yet. For now, there is only the slow red light, the outward drift of gas, the enormous and unhurried expansion of a star that has used its hydrogen and is finding what comes next. Millions of years pass between one moment and the next, in the way we are thinking about time here. The star does not rush toward any outcome. It inhabits each phase completely without looking forward. Perhaps this is something worth borrowing if you are still here and still listening. Not the timescale, which is not available to anything with a heartbeat, but the quality of inhabiting a phase without reaching past it. The star has no choice in this. You might or might not. Either way, it seems worth noticing that the reddening is not the ending, and the expansion is not a failure. And the slow change from one kind of light to another is, in the life of a star, simply what happens next. The red light continues outward in all directions. The core waits below, hot and dense and patient. The space around the star holds the drifting remnants of what it has shed. Everything is very slow, and the slowness is not emptiness. It is full of the same quiet the star has always kept. The inner planets go first. Not violently or all at once, but gradually, the way ice does not so much break as simply cease to be cold. The star has been expanding for a long time now, longer than any human unit of measure feels useful to hold. And the worlds that formed in its warmth so many billions of years ago are now finding themselves inside something they were never built to survive. Imagine you are drifting, very slowly, at a great distance. You are watching from far enough away that the star fills a portion of the sky that feels wrong, too large. The way a full moon looks through certain kinds of glass, distorted by proximity. The light coming toward you is not white anymore. It is deep orange at the edges, closer to red near the center, and it arrives with a quality that is less like illumination and more like pressure. The closest planet has already been consumed, though consumed is perhaps too sharp a word for what has happened. It did not burn dramatically. It encountered the expanding outer layers of the star, and then it was simply inside them, and then it was not a planet anymore. The difference between a planet and hot gas turns out, under certain conditions, to be a matter of time and temperature rather than a sharp border. The second planet takes longer. It sits in what was once a temperate distance, the kind of orbit that, around certain other stars, under other circumstances, might have allowed for liquid water. Here now, it is being unmade very slowly. Its atmosphere, whatever remained of it, has long since been stripped away by the stellar wind, that long breath outward that the star has been exhaling for thousands of years. What remains is the rock itself, and the rock is heating past any temperature that rock is meant to know. There is something worth sitting with here. These planets have existed for billions of years. They formed in the same spinning disk of gas and dust that formed the star itself. They are, in some sense, siblings, remnants of the same original cloud, the same ancient collapse. And now the largest of them is reclaiming what was always, in some loose sense, part of itself. The surface of the second planet, if you could somehow observe it closely without being destroyed by the observation, would be glowing. not with reflected light as it always did, but with its own heat. Rock becomes liquid at temperatures that are easy to state and difficult to truly picture. The planet is not cracking or exploding. It is softening. It is becoming something between solid and liquid, and eventually it will become something between liquid and vapor, and eventually the distinction will stop mattering entirely. The star does not notice. This is not indifference in any meaningful sense. It is simply that the scale of the star and the scale of the planet are so different that the planet's presence or absence changes nothing measurable about the star. A leaf falling into an ocean does not alter the ocean's depth in any way that matters to the ocean. Farther out, a third planet is still intact, though intact is generous. It is being sandblasted continuously by particles and radiation, its surface baking under light that is enormously more intense than anything that fell on it during the long, quiet years of the main sequence. If this planet ever had water, that water left long ago. If it had an atmosphere, what remains of it is thin and strange, altered by heat and radiation into something unrecognizable. Imagine you are watching the color of that planet change over thousands of years. Not a transformation you can see in a single moment, but one that, viewed across geological time, is steady and clear. The surface darkens, then it brightens again as certain minerals are exposed. The color shifts toward red and then toward something closer to gray, the gray of heated and recooled stone, the gray of material that has been through more than stone was built to carry. Somewhere farther out, the gas giants, if this particular star has any, are losing mass. Their upper atmospheres are expanding, escaping upward and outward, peeling away layer by layer over timescales that are long even by the star's standards. They are not being engulfed, not yet, but they are being slowly diminished. What was once a vast planet of swirling clouds is becoming, very gradually, a smaller vast planet of swirling clouds, then smaller still, the outer layers drifting off to join the general fog of stellar wind and scattered gas that now surrounds the whole system. This is the thing about destruction at these scales. It does not announce itself. It arrives the way autumn does, through accumulation of small changes, none of which alone would seem like ending. The light everywhere in this solar system is red. Not red the way sunset is red, with its suggestion of the day's end and the night's beginning, but a deeper, more settled red, a red that has been the color of this light for so long that if anything were still alive here, it would simply be the color light is. Red would be the color of an ordinary afternoon. There is nothing alive here, as far as we know. There may never have been, or there may have been something once in those long, stable years of the main sequence, on a planet at the right distance, under the right conditions. We cannot say. The The universe is old enough and large enough that questions like this do not resolve easily, and it is better to hold them gently than to answer them falsely. If there was life here once, it is long gone, ended or escaped or simply dissolved back into the chemistry of the planet that made it, which is now itself dissolving into the chemistry of the star. There is something neither sad nor comforting in this, only factual, a long chain of transformations that began in a molecular cloud and continues now, still continuing, with no final destination yet reached. The third planet crosses a threshold at some point, a threshold that is not sharp but that is real, and it begins to lose material in earnest. The rocky surface is heated past the point where rock remains rock in any useful sense. Silicates vaporize. Metals that have been solid since the planet formed are now moving, now rising, now joining the atmosphere not as gases that were always atmospheric, but as the planet itself, converting material that was the ground becoming something that drifts and disperses. This process is slow enough that it would be invisible to a human observer watching in real time. But you are not watching in real time. You are drifting here across deep time, letting the billions of years compress into something the mind can follow. And in that compression, you can see the planets thinning. You can see the inner system becoming emptier, quieter, less solid. A region of space that once held distinct worlds now holding only the star and its vast red envelope, and a scattering of material that used to be something else. The outer planets, if they are there, will survive this phase. They are far enough away that the star's expansion has not reached them yet, and the stellar wind, while stripping their outer layers, has not unmade them. They drift in their long, cold orbits, changed but present, smaller than they were, altered in ways that the billions of years have written into their composition, but still recognizably themselves. There is something in the way the whole system has rearranged itself that is worth staying with for a moment. What was once a star with planets is now a star that is reclaiming the space around itself. The boundary of the star is no longer a crisp surface at a particular distance. It is a gradient, a region where the density of stellar material decreases gradually, until eventually there is more space than star. And then the interplanetary medium takes over. And somewhere out there, the orbits of the outer worlds continue unchanged, as if the inner system were not being transformed entirely. The red light continues. It has been continuing for a long time, and it will continue for some time yet. The expansion of the star is not a single event, but a process with its own rhythm, its own pace, and that pace is slow enough that watching it requires a kind of patience that is easier to practice when you are not in a hurry, when you are resting somewhere comfortable, when the voice narrating this is itself unhurried, because the star is. The second planet is gone now, or rather it is still here in a different sense, its material scattered, absorbed, redistributed into the star's outer layers where it will travel outward with the stellar wind and eventually settle somewhere else, on some other journey in some other form. The planet did not end. It transformed. This is a distinction that may or may not feel meaningful, but it is accurate. The space where the inner planets used to be is still space. It is not empty in any pure sense, because the star's outer atmosphere extends through it, and particles and photons move through it constantly. But there are no solid worlds there anymore. There is only the star, and its long red light, and the slow outward drift of gas that was once a boundary and is now a region, and then a gradient, and then eventually just the star's influence spreading quietly outward into whatever comes next. For now, the light is red, and the gas drifts, and the outer planets carry their cold orbits forward in the dark at the edge of the system, and nothing here is hurried, and there is no need for you to be either. The outer layers are already moving. They have been moving for some time, gradually, the way a breath leaves a room through an open window rather than all at once. The star has been shedding material for thousands of years before this moment, a slow exhalation of gas and dust riding outward on the stellar wind. But now, at this stage, the shedding accelerates. The core contracts further, and the outer envelope, loosely held, begins to separate in earnest. This is not an explosion. It is worth saying that clearly, because the word sometimes arrives before the image does. This is a release, not a rupture. The gas simply goes, lifted by radiation pressure and the gradual weakening of the star's gravitational grip on its own outermost material. Imagine you are watching from a great distance, far enough to see the whole system at once. What you would see is a brightening, a slow blooming of faint color around what used to be a point of light. The shape it takes depends on many things. Some planetary nebulae are nearly spherical, a soft glowing ball of gas that expands evenly in all directions. Others are elongated, stretched into bipolar lobes like two soap bubbles pressed together at their centers, the result of a binary companion or a magnetic field or a fast inner wind catching up to a slower outer one. Others are ringed or layered or knotted with dense clumps of gas that have cooled and condensed as they traveled outward. The diversity is quiet and real. No two are arranged in exactly the same way. This star's nebula is beginning to take its own shape. The gas that left first is already far out, cooler, dimmer, thinning as it spreads. The gas that is leaving now is brighter, faster, driven by a hotter phase of the star's wind. The two layers will interact where they meet. the faster gas compressing the slower gas ahead of it into a shell, the way a wave gathers water as it moves. That shell will glow. Different parts of it will glow in different colors, depending on their temperature and composition, and how much ultraviolet light the central star is pouring into them. Imagine you are drifting inside the nebula itself, somewhere between the central star and the outer edge. The light here is not white. It is colored in ways that have specific causes. Green in some regions, from oxygen atoms that have lost 2 electrons and are slowly recapturing them, releasing energy in a wavelength the eye reads as a kind of cold green. Red and pink in others, from hydrogen atoms doing something similar. Blue closer to the center, where the radiation is harder, more energetic, where the gas is hotter and atoms are more completely stripped. The colors are not decoration. They are a record of what is happening at each distance, each temperature, each density. You are reading the nebula as you drift through it, whether you mean to or not. The central star, now exposed, is very hot. What remains of the star's core is a remnant that will eventually become a white dwarf. But for now it is still contracting, still radiating intensely, its surface temperature climbing into ranges that produce ultraviolet light in enormous quantities. This ultraviolet light is what ionizes the surrounding gas, what makes the nebula glow. Without it, the gas would simply drift outward in darkness. With it, the gas becomes luminous, a self-displaying record of the star's passage out of its long life. The name planetary nebula has nothing to do with planets. It was given in the 18th century because through early telescopes, some of these objects appeared as round, greenish disks, reminiscent of the planet Uranus. The name carried forward as names do, long after its original reasoning became obsolete. There are no planets forming here, and no planets involved in the process, though it is possible that any surviving outer planets are now embedded in this expanding cloud, slowly being bathed in material that was once the interior of the star that made them. Think about what that means slowly, without urgency. The gas drifting past those cold outer planets contains oxygen and carbon and nitrogen, elements forged over billions of years in the star's nuclear burning, elements that were locked inside the star since before the planets formed. Now they are free. They will travel outward with the nebula as the nebula continues to expand, and the nebula will eventually thin to the point where it disappears from view, not because the material is gone, but because it has become too spread out, too faint, too diffuse to be detected as a coherent structure. Most planetary nebulae persist for roughly 10,000 years as visible structures. That is a long time by most measures, and a brief breath by the measures we have been using here. 10,000 years from now, or 50,000, the nebula will be gone in any practical sense. The material will still exist, dispersed into the interstellar medium, mixing with the gas and dust that was already there, becoming part of the general substance of the galaxy. Other stars will form from that material someday, other systems. The oxygen that was forged here may eventually find its way into water on a planet orbiting a younger star. The carbon may become part of an organic molecule. This is not a poetic exaggeration. It is, as best we understand, what happens. The material moves, it waits, it joins other material, it becomes other things. For now, though, it is still the nebula. It is still this particular expanding shell. Imagine you are watching it from outside, from a position far enough away that the whole structure fits in your field of view. The central star is a point, faint and blue-white, surrounded by the glowing cloud. The cloud has a texture to it, subtle variations in brightness, places where the gas is denser, places where it is thinner. The colors shift across the face of it. At the edges, the material is cooler and the light is softer. At the center, near the star, the light is harder, brighter, more energetic. There is a kind of silence implied by all of this. Not actual silence, because in the right frequencies there is radio emission, there is infrared, there is ultraviolet. But in the frequencies available to the human eye, and especially at this distance, and especially in the slow frame of time we have been keeping, the nebula seems quiet. It expands at perhaps 20 or 30 kilometers per second, which is fast in terrestrial terms and nearly motionless against the scale of what we have been watching. Over a human lifetime, the outer edge of a typical planetary nebula moves outward by an amount that would be difficult to measure without precise instrumentation. This is what slow looks like, even at its faster moments. The clumps and knots in the nebula are worth a moment of attention. Some planetary nebulae contain dense concentrations of gas, sometimes called cometary knots because they trail faint tails away from the central star, pointed outward by radiation pressure. These knots are denser than the surrounding gas, cooler, harder to ionize. They persist as the nebula expands. Some astronomers have speculated that material in these knots could eventually seed new star formation, that the density is already doing quiet preparatory work. This is uncertain and worth holding loosely, but the idea is not unreasonable. The core continues to contract below all of this. It is not participating in the nebula in any structural sense. It is the source of the ionizing light, the lamp inside the shade, but it has its own process underway, separate and interior. The electrons and ions of the collapsing core are pressing toward each other, Gravity is still working. The outcome of that contraction is the subject of what comes next. But for now, it is enough to say that the core is becoming something very small, very dense, very hot, and that it will burn for a long time in its own quiet way. Let the nebula hold your attention for a little longer. The colors are fading at the edges, not because anything has ended, but because the gas there is cooling and thinning, and the light reaching it is weaker. The central regions remain bright. The structure as a whole is still coherent, still recognizable as the outer layers of a specific star, though it no longer resembles a star in any obvious way. It resembles instead a kind of record, a three-dimensional inscription left by something that happened here, something that took billions of years to build toward this moment. The gas drifts outward, a few wisps separate from the main structure and travel further, thinning faster. There is something restful about an object that is doing exactly what it must do, according to the physics of its own composition, in its own time, without any additional cause being required. The nebula is not trying to go anywhere. It is simply going. The gas at the outer edge is slightly cooler than the gas that will reach that edge later. Each shell records its own moment of departure, its own brief chapter in a sequence that needed no observer to unfold. You do not need to keep track of all of it. It is enough to rest here, at this scale, in this soft-lit, expanding cloud, where the colors are real and the motion is slow, and the star that made all of this is still faintly visible at the center, a point of blue-white light doing its quiet work, illuminating the record of its own long life from the inside out. The gas continues to move. It will move for a long time. There is no particular moment when this ends. What remains is small and white and very far away. After everything that came before, after the long hydrogen burning and the slow red swelling and the gentle release of the outer layers into the dark, what is left is roughly the size of Earth. Not Earth as a dramatic comparison, but Earth as a simple unit of measurement. A sphere, approximately that large, sitting in the place the star once occupied, glowing faintly in wavelengths that lean toward blue-white, the color of something extremely hot but not extremely bright, because it is small, and small things, however hot, do not fill much of the sky. Imagine you are drifting toward it slowly, across a distance that takes light itself several years to cross. From here it looks like a point. Nearly everything at stellar distances looks like a point. But if you could resolve it, if you could sharpen the view until the geometry became clear, you would see a sphere with no atmosphere worth speaking of. No convection, no magnetic storms, no visible eruptions. Just a surface radiating heat. The surface temperature of a young white dwarf can be well above 100,000 degrees, and yet the object seems quiet, because temperature and brightness are not the same thing, and this thing is very small. It will cool for a long time. That is, in some ways, the entire story of what comes next. The white dwarf has no fuel. It is not fusing anything. It is not contracting significantly, because a kind of pressure that has nothing to do with heat, a quantum mechanical resistance that electrons have to being compressed into the same space, holds it up against gravity. This pressure does not require energy to maintain. It is simply a property of matter arranged this way. The white dwarf holds its shape not because anything is burning, but because the universe does not permit electrons to behave otherwise. So it sits and it radiates, and what it is radiating is not new energy but old energy, stored in the heat of its own body, leaking slowly outward into the dark. Imagine you are very still, watching something cool the way you might watch a piece of iron after a fire has gone out. Not suddenly, not all at once, but steadily over time from the outside inward, the temperature dropping in fractions, the color shifting as it goes. A young white dwarf is blue-white. An older one, having cooled over billions of years, shifts toward yellow-white, then white, then, in theory, yellow, then orange, then the deep reds, and then eventually something that emits very little visible light at all. That final stage, a cold, dark sphere drifting in space, is sometimes called a black dwarf. No black dwarf is believed to exist yet in this universe. The universe is not old enough. Even the oldest white dwarfs, those that formed in the first billion years of cosmic history, have not had time to cool that far. The process is that slow. This particular white dwarf, the one at the end of this particular star's life, is young, cooling, but young in the way that means it has perhaps 10 trillion years ahead of it before it becomes truly dark. 10 trillion years is not a number that rewards effort to visualize. It is simply a span of time so large that everything familiar recedes into it and disappears. Hold it lightly. The composition of the white dwarf is mostly carbon and oxygen, layered in a dense core, with a thin outer layer of helium, and above that a thinner layer still of hydrogen, if any hydrogen settled there after the outer envelope dispersed. The carbon and oxygen at the center may, over long periods of cooling, begin to crystallize, the atoms arranging themselves into a lattice the way water arranges itself into ice, but at densities and pressures that have no everyday comparison. In this sense, the white dwarf is becoming, slowly, a crystal, though the word does not fully capture what happens to matter at that density and temperature. There is no sound. There has been no sound at any point in this story, because sound requires a medium, and the medium between stars is too thin to carry it. But here the silence feels different, more final, not because anything dramatic has concluded, but because the processes that generated light and heat and motion over billions of years have now simplified themselves to a single patient one: cooling. Imagine you are drifting at the same distance but slowly circling, the way a probe might orbit a distant body, and you are watching the white dwarf across time rather than across space, watching it the way you might flip through images taken over millions of years, each one nearly identical to the last. In the first million years, the color shifts are subtle. The surface cools from the outer layers inward, but it is still extremely bright by the standards of anything you could stand next to. The light is steady. There are no flares, generally, no cycles, no seasons. Some white dwarfs do pulsate, oscillating in brightness as waves move through their interiors, and some accrete material from a companion star if one exists nearby. And in rare cases, that accretion leads to a thermonuclear surface explosion, a nova, or in rarer and more specific circumstances, a total detonation. But for a white dwarf cooling alone in space, with no companion, there is only the long quiet. The surface dims. Over hundreds of millions of years, the color moves toward white, and then something cooler. The star this white dwarf came from was average enough that no one would have marked its death as remarkable. The gas it shed has long since merged with the larger interstellar medium, contributing its carbon and oxygen and nitrogen to the reservoir from which future stars will eventually form. In that way, the star is not entirely gone. Its matter persists, scattered and diffuse, waiting in the dark for the slow gravity of a future cloud to gather it again. But the white dwarf itself does not scatter. It holds. That holding is one of the quieter facts in all of astrophysics. A white dwarf, absent some external catastrophe, will persist essentially forever on any timescale that involves stars and planets and the things that form around them, long after the sun has finished its own version of this story, long after the last red dwarf stars have burned through their small fuel reserves over timescales of trillions of years. White dwarfs will still be cooling in the dark, cooling toward temperatures we have not yet observed, toward a darkness the universe has not yet produced. Imagine you are no longer trying to keep track of the years. The white dwarf does not require your attention to continue cooling. It will do this whether observed or not, whether the universe contains anything capable of observation or not. The physics is simple and it is patient, and it does not need to be dramatic to be true. There is a certain kind of rest in watching something that requires nothing from you. Not because it is beautiful, though it is, in a subdued and colorless way, a small white point in a vast dark field, the last light of something that once burned for billions of years, but because it is simply doing what it is, cooling, holding, persisting. You can let your attention soften here. The white dwarf is approximately as massive as the sun was, compressed into a volume approximately as large as the Earth was, and it is drifting through the galaxy on roughly the same orbital path the star followed, because momentum is also conserved. Because the universe does not forget where things were going. It will orbit for a long time. It will pass through regions of denser gas and regions of emptiness. It will feel the gravitational company of other stars at great distances. It will not react to most of this. It is too dense to be easily disturbed. The galaxy itself will change around it. Stars will form and evolve and end. Spiral arms will wind and shift over billions of years. Galaxies will merge. The shapes we see when we look up will become unrecognizable over timescales long enough. But the white dwarf will persist through much of this, a small cold point, carrying its crystallizing interior and its thin outer layers and its quiet inward cooling across whatever the galaxy becomes. You do not need to follow it that far. This is enough. The cooling is enough. The fact that it holds its shape without burning is enough. The fact that it carries in its composition the record of the star it came from, the carbon forged in helium fusion, the oxygen layered within, the physics of its formation written into its density and its temperature and its slowly crystallizing core. These facts are not urgent. They are simply true, and they are true at this moment. And they will be true for longer than we have language to describe. The white dwarf drifts. The dark around it is very large, and the dark is mostly quiet, and the white dwarf is cooling in it at a rate too slow to watch directly. The way ice forms on a still pond when the temperature drops just barely below freezing. The change happening at scales smaller than sight, accumulating into something only measurable over time. You can close your eyes if you like. The cooling continues without you. The white dwarf does not notice the absence of observation. It is not lonely, because loneliness requires the capacity for it. And the white dwarf is dense matter cooling according to well-understood physics in an empty region of a middling galaxy. And that is exactly what it is. And that is enough. And it will go on being enough for longer than you need to think about right now. The dark is steady. The light, small as it is, holds.